Bismillah, Alhamdulillah, Salatu Wassalamu ala Rasulillah. This is section 1.7, and it's about some types of matrices, diagonal matrices, triangular matrices, and symmetric matrices. So, what are diagonal matrices? A square matrix in which all the entries of the main diagonal are zero. So, the entries that are not on the main diagonal, of the main diagonal. So not on the main diagonal, are zero. So don't look to the diagonal entries. Forget about the diagonal entries. The diagonal entries could be zero or non-zero. There is no problem. But the entries of the main diagonal, above the main diagonal and below the main diagonal, should be all zeros. So these are all examples of diagonal matrices. Notice here, we don't pay attention to the main diagonal. It could be zeros or non-zeros, but of the main diagonal above and below are zeros. So it is considered as a diagonal matrix. How to find the inverse of a diagonal matrix? That's very easy. You just find the inverse of the numbers or the entries on the main diagonal. So what is the multiplicative inverse of 1, or the reciprocal of 1 is 1, and the reciprocal of -3 is 1 over -3, and the reciprocal of 2 is 1 over 2. Just the reciprocal, the multiplicative inverse. So now if you multiply A times A inverse, or A inverse times A, you will get the identity matrix. So in fact, this is the inverse matrix. Powers of diagonal matrices. Also, it's very easy to find the powers of diagonal matrices. For example, if you want to find A cubed, you don't have to multiply A times A times A 3 times. It's enough to raise each entry on the main diagonal to the power 3. So 1 to the power 3 is 1. -3 to the power 3 is -27. 2 to the power 3 is 8. So if you multiply A times A times A 3 times, you will get this answer. So it's very easy to find inverse and powers of diagonal matrices. So even if you want to find A to the power -100, it would be 1 to the power -100 and -3 to the power -100 and 2 to the power -100. That's it. As easy as that. This is about diagonal matrices. What about triangular matrices? We have upper triangular matrices and lower triangular matrices. Pay attention to the definition. A square matrix. So again, we are dealing only with square matrices up to now in this section, in which all the entries above the main diagonal are zero. So above the main diagonal, the entries should be zero. What about the main diagonal itself? Nothing mentioned. What about the entries below the main diagonal? Nothing mentioned. So only the entries above the main diagonal should be zero. Then we call it lower triangle. So this matrix is a lower triangular because the elements above the main diagonal are zero. If the entries below the main diagonal are zero, then we call it upper triangle. So look below the main diagonal. So for example, this matrix If you look above the main diagonal, it is 0. If you look below the main diagonal, 0. If you look off the main diagonal, you have zeros. So in fact, this matrix is diagonal, and it is upper triangular, and it's also lower triangular. It satisfies all the three conditions. So you need to understand the definition very well. Also, you can observe that any diagonal matrix is upper triangular because the elements below the main diagonal are zeros, and it's lower triangular at the same time because the entries above the main diagonal are zeros, because this is the definition of the diagonal matrix. All entries of the main diagonal are zero. So any diagonal is upper triangular and lower triangular at the same time. Now let us look to this theorem. The transpose of a lower triangular is upper triangular, and the transpose of upper is lower. The product of lower triangular matrices is lower, and product of two upper triangular matrices is upper. A triangular matrix is invertible. This is important if and only if its diagonal entries are all non-zero. So if you have a triangular matrix and you want to know whether it's invertible or not, look to the entries on the main diagonal. If they are all non-zeros, then it is invertible. So for example, this matrix, the zero matrix, is not invertible because the elements on the main diagonal are zeros. The inverse of an invertible lower triangular is lower, and the inverse of invertible upper is upper. Let us solve this example. We have two upper triangular matrices because the elements, the entries below the main diagonal are zeros in both cases. But what about A inverse? Can we find A inverse? Is A invertible? Yes. Why it's invertible? Because the elements on the main diagonal are non-zeros. But is it easy to find A inverse? Well, what we know that the entries on the main diagonal, we know that the inverse is upper triangle. So we will have zeros here. Okay. We also will see this fact that the entries on the main diagonal, we will have the inverse, the multiplicative inverse of the numbers. So I have 1 here and half here instead of 2, and 1/5 here instead of 5. But what are the other entries? I don't know. I have to find out. I have to use the method that we know, we mentioned before, how to find the inverse of a square matrix. You write the matrix here and the identity matrix here, and you work with this matrix, change it to the identity, and then this matrix would be changed to A inverse. I have 1, 0, 0, that's good. Now this 2, I need it to be 1, so I will divide R2 by 2, and I will have this matrix. Now I'll use this one, the leading one. Also, I can divide R3 by 5 at the same time because I have 0 here, so that's good. Oh, when I divide 5 by 5, the answer should be 1. Good. So I divided the second row by 2 and the third by 5 at the same time. Now I have 1 here. I'll use it to make this 3 0. So negative 3R2 plus R1. There is no change in the second row. Okay. Also, this 0 will not change, and this 0 will not change, and this 0 will not change because I'm using row 2 to change row 1. So any 0 in row 2 will not change anything in row 1. Now, negative 3 plus 3, that's 0. Negative 3 times 2 is negative 6 minus 1, that's negative 7. And negative 3 over 2 plus 0. And now let us use this one to make 2 and negative 7 zeros. So negative 2 R3 plus R1 and 7 R3 plus R1. This is plus R2. Negative 2 R3 plus R2. So the new matrix would be, there is no change in the third row. And I'm using the third row to make zeros. So any 0 in the third row will not change anything in other rows. Okay, negative 2 plus 2, that's 0. Negative 2 over 5. And now 7 minus 7 is 0. And 7 over 5. So this is A inverse. I have 1, 1 over 2, 1 over 5, as we mentioned here. And this is negative 3 over 2. And this is 7 over 5. And this is negative 2 over 5. And you can check this answer. If you multiply A times A inverse, or A inverse times A, you will get the identity matrix. So for the triangular the upper triangular or lower triangular, it's not that easy to find A inverse. It's easier than a usual matrix, but you need to do some work. You need to use this method. But you know at the end that the elements, the entries on the main diagonal are reversed. The inverse, you have the reciprocal. Now, notice that B inverse does not exist. B inverse does not exist because I have a 0 here. Okay, so the reciprocal of 0 is math error. And we can find A times B if you like. So A times B, we said that the product of two triangular matrices is a triangular matrix. So let us check that. Multiply this row times this column, so you will get 3. And this row times this column is negative 2. And this row times this column is 2 minus 3, that's negative 1, minus 1, that's negative 2. Now the second row will give you 0. The second row times the second column will give you 0. The second row times the third column will give you negative 2 plus 4. That's 2. Now the third row will give you 0, 0, 5. Notice that this matrix is a square matrix. And of course, it's a square. It's also upper triangular. And notice something else. The product of AB, look to the main diagonal. It is the product of the entries on the main diagonal of A and B. So 1 times 3, 2 times 0, 5 times 1 will give you these entries. So if you try to find VA, sure, now we know that it is a triangular matrix, upper triangular matrix. So I'll have zeros here. And also the product of the entries on the main diagonal would be the product of the entries on B and A. So I'll have here 3, and here 0, and here 5. So all what I need to find are these three, the remaining three entries. So this entry, to find this entry, I need to multiply the first row of B by the second column of A. So I'll have 9 minus 4, and that's 5. And here, to have this entry, I need to multiply the first row of B by the third column of A. So negative 3 minus 8, negative 11, plus 10, so that's negative 1. And finally, this number, it is in the second row, third column. So multiply the second row of B by the third column of A. So I'll have negative 5. And you can notice that AB is not equal to BA also in this case. So observe that in this example, the diagonal entries of AB, BA are the same, 305, 305, and are the product of the corresponding diagonal entries of A and B. So this is what I mentioned. You multiply 3 times 1 and 0 times 2 and 1 times 5 to get the diagonal entries on AB and BA. And also, the diagonal entries of A inverse are the reciprocals of the diagonal entries of A. So this is 1, this is 1, this is 2, this is half, this is 5, this is 1 over 5. Okay, the third type of matrix is symmetric matrices. We call a matrix a square matrix, so all matrices in this section are square. It is symmetric if A equals AT. AT, the transpose of A, changing the rows into columns. So if you find the transpose of A and it's equal to A, we call A a square symmetric matrix. We call A a symmetric matrix. So here, if you find the transpose of this matrix, it would be 7, negative 3, the first row, write it first column, and the second row, write it second column. Now, compare these two, they are equal. So it is a symmetric matrix. So this is symmetric, this is also symmetric, and this is also symmetric. How to figure out without finding the AT, the transpose? Well, forget about the entries on the main diagonal. Look to the entries here. Negative 3 and negative 3, these two should be equal. Here, for example, forget about the main diagonal. You have 4 here, this should be 4, 5, 5, 0, 0. So this is what would happen if you have a symmetric matrix. Here also, forget about these, the main diagonal 0, 0, 0, 0, 0, 0, 0, 0. All of these entries should be the same. Then we call it a square matrix. Now, an example of a square matrix is 8 times AT and AT times A. If you bring any matrix A, any matrix, for example, this matrix, this is a 2 by 3, it's not a square matrix. So it's not symmetric by itself. But A times AT would be symmetric, or AT times A also would be symmetric. So if you find A times AT, A is 1, 3, negative 2, 0, or negative 5. This is A. Multiply by AT. Write the first row as first column and the second row as second column. Now, always when you multiply A times AT or AT times A, you will have a square matrix. That's also symmetric. Here I have 2 rows and 3 columns. Here I have 3 rows and 2 columns. So the product will give you 2 by 2. While AT times A will give you 3 by 3. Both would be symmetric. So let us find the product, multiply this row times this column. 1 plus 4, 5 plus 16, 21. The first row times the second column, 3 minus 20. so negative 17. The second row by the first column, 3 minus 20, that's negative 17. The second row by the second column, 9 plus 25, that's 34. So notice that this matrix is symmetric. Why? Because forget about the main diagonal, you have negative 17 here and negative 17 here. So A would be equal to A transpose, not A, I mean, if you call this matrix B, B would be equal to B transpose. So if you need an example about symmetric matrices, remember always A times AT will give you a symmetric matrix. Some exercises: classify the matrix as upper triangular, lower, or diagonal, and decide whether the matrix is invertible or not. Okay. This matrix, forget about the main diagonal. I have 1 here and 0 here. So it's upper triangular because I have 0 below the main diagonal. Is it invertible? It is invertible because the entries on the main diagonal are not zeros. That's it. Okay. This matrix, forget about the main diagonal. I have 4 here and 0 here. So it's lower triangular because I have a number here while this is a 0. So above the main diagonal zeros. It's not invertible because I have zeros on the main diagonal. So the inverse does not exist. This is a diagonal matrix. And since it's diagonal, I have zeros above the main diagonal, so it's lower triangular. And I have zeros below the main diagonal, so it's upper triangular. And it's invertible because I have non-zeros on the main diagonal. Here, this is an upper triangular because I have zeros below the main diagonal. And it's not invertible because I have 0 on the main diagonal. Find A square. Okay, A square would be, this is a diagonal matrix, so just square the entries here. So of the main diagonal, so 1 over 0, 1 over 9, and 1 over 16. This works only if you have a diagonal matrices. Okay, you can find A square easily. Otherwise, you need to multiply A times A. A to the power negative 2 would be half to the power negative 2. So it would be, or it would be the inverse of A square. Okay, so it would be 4 here, 9 here, and 16 here. So it's just the inverse of this one. So the reciprocals of the entries on the main diagonal. A to the power minus k would be half to the power minus k, 1 over 3 to the power minus k, and 1 over 4 to the power negative k. And you know that whenever you have a over b to the power negative 1, this is in fact b over a. So you can write this as 2 to the power k, because half to the power negative 1 is 2. And this would be 3 to the power k. And this would be 4 to the power k. This looks better than this one and easier to understand. Compute the indicated quantity. Well, this is a diagonal matrix, so it's easy to find the powers. So it's just 1 to the power 39 and negative 1 to the power 39. So 1, 0, 0, negative 1. Because negative 1 to the power 39 is negative. So it's in fact will give you the same matrix. What about this one? create a symmetric matrix by substituting appropriate numbers for the x's. So this is the main diagonal. I have 3 here, so this number should be 3. I have 7 here, so this number should be 7. I have -8, so this number should be -8. 2, so this number should be 2. I have 3, so this one should be 3, and 9 here. So these should be the numbers to make this matrix symmetric matrix. Is this matrix invertible? It's a lower triangular. Look to the enters of the main diagonal, non-zeros. So yes. Okay, there is no yes. I'll just mention invertible, because all the enters on the main diagonal are not zeros. Find all values of the unknown constants for which A is symmetric. Well, forget about the enters on the main diagonal. Now, A plus 5 should be equal to -3 to make this matrix symmetric. So A is -8. So this is the answer. This is the value of the unknown, which is A, for which the matrix is symmetric. Find all values of X for which A is invertible. Well, A is invertible if X minus 1 is not 0, and if X plus 2 is not 0, and if X is minus 4 is not 0. The enters on the main diagonal shouldn't be zeros, because I have an upper triangular matrix. So the values, all values of X for which A is invertible, X shouldn't be equal to 0, and shouldn't be equal to -2, and shouldn't be equal to 4, and all other numbers except, sorry, this is 1, X, when you take 1 to the other side. So X could be any real number except 1, -2, and 4. This was the last example. I hope you enjoyed listening to the recording of this section.